Okay, spectrum of AB up to zeros coincide with spectrum of BA upside to 0. And additionally, if one of operators have inverse, then the spectrum are coincide. Was this formulation or not? An additional. If one of operators has bounded inverse, inverse, then it is very easy because in this situation, AB is similar to BA. I prove first this additional formulation. If at least one of operators has inverse, then operators AB and BA are similar. We prove that spectrum of similar operators are coincide. Yes? Why? Let exist A minus 1. Multiplicate it on identity from the right and write this identity as A minus 1. And what you see?
Okay. They're similar.
They're similar. AB, BA are here in inverse operator.
The same spectrum.
Yes?
Oh, okay.
But this is more difficult situation. So let lambda not 0 and lambda belongs to the resolvent set of BA. I hope it is clear that you can reformulate this statement in terms of resolvent set. It is the same. It is the same. So let lambda is not 0. Lambda belongs to the resolvent set. For example, lambda, we know if lambda less greater than it is from the resolvent set, yes? Okay, we must understand why it belongs to here. Let's try to write this inverse operator. For large lambdas, how it looks like. Neumann representation for resolvent. Minus 1 lambda A, B, K, lambda K. It just I write only formally without proving anything. But then we write such formula for which you can guess, but it is difficult. You can say I dream it, but it is difficult. So I obtain this formula without any argumentations, without strictly proof. But then we can take away all middle calculations. How you can write it? Identity plus AB plus AB, AB plus etc. Oh, sorry, lambda, lambda square, etc. What you can do for all these part? All these terms has A at the first place and B at the last place. Yes? So you can write it in the form And what we have here, this with this. Inverse operator for BA. For BA, but here B. And up to the sign, yes, because here minus, so it is minus. Minus A, resolvent of operator BA, B. That's all. Then you can take away all these formulas and say, for me or for yourself, I guess that the resolvent for AB looks like here via resolvent BA. So you can take away these assumptions because we obtain formula without any series. If you assume only this and this, you can write the resolvent for operator BA. And let's say, I guess that the resolvent for AB can be obtained by this. But how to guess? It is difficult. But with the series, we can obtain. Here no series. And you can just check by multiplication that it is indeed the resolvent. So if existed, say exists AB. And this is some analogous, it is in physics formula Lippmann-Schwinger, if I don't miss anything. But I think it's just, have a connection with Lippmann-Schwinger formulas in operator form. And inverse, if you, of course, you can begin from the, so what you can say about the resolvent BA in the following formula. Minus 1 over lambda I minus B AB A. So changing K, B by places. That's all. And you can see, so if one is operator invertible, then this operator make them similar. Yes, just this operator make them similar. And example that this different sets, it's our operators shift right and left shift. So R A left, right and left. Right, put 0 on the first place, then come back. So it is identity. So spectrum equals from 1. Yes? And another A first shift to the left, then come back to the right, and on first place we put 0. We put 0, x equals 0, x2, x3, and so on. So it is projector on the orthogonal complement to the first basis vector. What we know about projection? Do I give you a task on spectrum of projector? No? But we have 11 tasks, so it's a lot of. But spectrum of projections, later we show it. Today we discuss it. The spectrum of projection is 2 points, 0 and 1, for non-trivial situation. If it is projection on non-trivial subspace, then the spectrum of any projection is 0 and 1. So you see that spectrum are different. But up to this element, they are the same. Mm-hmm. Okay? So, what we additional need to discuss?
So sorry, before next question.
Mm-hmm.
This one proved they have the same spectrum. What about the classification of their?
About classification, and in this situation they coincide. Yes, in this they coincide. I don't know, but I suppose that they are the same. That they are the same spectrums. So,
if we have a compact.
Okay. Okay, but if we want to discuss this, First, we need to give an answer on spectrum of this operator in L2. There was a problem, yeah?
Yes.
What we can say about this spectrum? What we can say about this spectrum, the spectrum of this operator, of such operator?
It's not
Spectrum of operator multiplication on bounded sequence.
I try to find these simultaneously with the factorial.
Okay, let's try. Point spectrum is easy to find. If you want to find A alpha x equals to lambda x, then for any k, alpha k xk equals lambda xk, yes? And if you have non-zero coordinate xk, is not zero, then immediately lambda equals to alpha k. For example, for this basis vector ek, which one stays on the kth place. One stays on the kth place. Then, of course, it is alpha k ek. And if all xk are 0, then it is not eigenvector. Yes? If all xk are 0, there we have no eigenvector, because eigenvector is not zero vector. So necessary we have this for eigenvector. There must exist such coordinate that is not zero. Then we immediately obtain this.
Okay.
So point spectrum is all these numbers. Then remember Boltzmann theorem, yeah? From calculus, mathematical analysis. Our sequence alpha is bounded. It always have limit points. And spectrum is closed space. So we immediately obtain that this is set, the closure is in spectrum, because spectrum is closed. Let's come back on 5 minutes later, before. We consider such operator. X1, x2 over 2, x3 over 3, and so on. What is the alpha k? What is the alpha k? 1 over k. Yes? So point spectrum is sequence 1 over k for all k from 1 to infinity. But 0 lies in this set, because the limit of these elements is 0. So 0 is in spectrum too. So the limit points, there are different situations. Limit points can be some number from this sequence. Yes, it may be closed sequence. But another situation when limit points do not belong to this. So the limit points are in spectrum too, because spectrum is closed set. Okay? But what you can do following. I claim that this equality. You can show that here equality, that it's all spectrum. So all numbers alpha k and its closure. Why it is whole spectrum? Let lambda not belongs to the this set. It is closed set. Then distance to this set is positive. So infimum for all k of the difference alpha k minus lambda equals to some positive number d. Because lambda do not belong to the closed set. Doesn't belong to the closed set, yes? So you immediately can construct and show that it is exists bounded resolvent. How, if you write this equation in coordinate, how you can find xk? Resolvent, how it works? We must divide on this sequence, yes? It is again the operator of multiplication on U sequence, on this sequence. What is the norm of operator of multiplication on sequence? We show it, we calculate it. It is supremum of these numbers. But this supremum equals to 1 over infimum. But this is positive number. So it equals 1 over d, it is finite. So we show that spectrum is just all this set. Yep. And now come back to your problems, to the next problem. Let's take some compact on the complex plane. Let omega be compact in complex plane. Can I find countable dense set in omega? It is compact. For any epsilon, you have a finite epsilon network. For any 1 over n, you have finite network. Yes? For any n, exist finite 1n network. It's y n1, yn2, yn, mn. Yep. For any n, you have finite. The number up is the number of step, for example, or number of this epsilon. What you can say about the union over n? What is the power of this set? For any n, it is finite, countable. Is it dense in omega? Is it dense? It's countable and dense. Renumerated is alpha 1, alpha 2, alpha 3, and so on. As it is countable, you can numerate it, yes? In one order. In one order. In one numeration. Here we have two numerations, yes? We have first we have number here, and then we enumerate finite elements for this fixed n. But it is countable, so we can enumerate it as alpha 1, alpha 2, alpha n. Consider the operator multiplication on this sequence. What is the spectrum? Omega. Because we obtained that it is alpha k and closure. So that's all. That's all. We enumerate and then go to the operator A alpha. The more difficult construction when all points of spectrum are point spectrum. It is more difficult. Let U adjoint coincide with inverse. It's a unitary operator. Then spectrum of U lies in this set. First, the norm of operator equals to 1, yes? We know it. The norm of unitary operator, from definition of it is B action which preserves scalar product. So it is B action which preserves norms. So the norm of unitary operator is 1. So for any lambda with such absolute value, we immediately take that this lambda from what space? Resolvent set. So it is belongs to resolvent set of U. Second, let this operator has inverse. Moreover, and this norm equals to 1 because the norm of operator and adjoint operator equals to 1. And norm and I can see on this operator as a perturbation of invertible operator. So it has inverse. So if lambda greater than 1, it is inverse. Is less than 1, it is inverse. So where spectrum can be? Only on unit circle. And you can construct operator for any compact on unit circle. For any compact on unit circle, there exists unitary operator with such spectrum. The same idea. Okay. So you take only the dense set on the unit circle. Okay, yeah? So, and then we consider operator which is self-adjoint and unitary. So by all properties of spectrum, where can lie spectrum? Spectrum can be minus plus 1, yes? Plus 1 and minus 1. If U equals U star equals U minus 1, here is real spectrum. And here modulus lambda equals 1, yes? So intersection of two sets. Intersection of real axis with the unit circle. 2 points. Possible numbers in spectrum, only 2 points. But can we realize this situation or not? So let's consider an interesting thing. What you can say about this operator? It is identity. It is identity. Let's calculate the square of this operator. I minus 2u plus u square over 4. What you can say about the square of operator? Operator is invertible to itself. Operator is inverse to itself. So what is u square? Identity. This identity. So we have 2 identity minus tie u divided on 4. So it is 1 identity minus u divided on 2. So it is a projection. And so additional is a projection too. Additional operator is a projection too. And in sum, they give us all space. Let's consider the vector from image of operator, of the first operator. So let's range of E minus U over 2 equals to H0. Yes? It's a projection on H0, and this is projection on another space, on the complement space. So by definition, yes, for any x from H0, because it is a projection. Because it is a projection. So the eigenvectors for what eigennumber? Minus 1. Minus 1. And for any x from the range of this operator, by the same arguments, we obtain plus 1. So that this is H1. So we defined H0 plus H1. And in this block representation U, minus 1, 0, 0, 1. So all space divided on two subspaces. On one we obtain minus 1 by projections, on another 1. Maybe some spaces be trivial. Maybe, but it's possible. For example, identity is the part of this operator. For identity, H0 is 0. Oh, no, sorry. For identity, H0 is 0. And H1, just identity on whole space. Maybe H1 be 0 subspace. Then your operator U is minus identity. And in general situation, in general position, the combination of identity and minus identity on some subspaces. The main idea is to guess that this is projections, which gives us whole space, because sum of is identity. So let's prove that the spectrum of projector is 0 and 1, and find the resonance. So problem is, so in arbitrary Banach space. So X is Banach. We decomposed it in two subspaces, X1 and X1 are closed. I remind that the closest of subspaces we need for boundedness of projection. Projector is bounded operator if and only if all two subspaces are closed. And P is projection X on X0 along X1. Along X1. So any vector can be composed, represented as sum of two components, and Px equals to X0. This is a long definition of projections. Yes. So problem, spectrum of projection and resolvent. And find the resolvent. Let's try find eigenvectors. Again, as at linear algebra. So first, by definition of projections, I can rewrite the problem for eigenvalues in the following form. By components in this space. Then how we can recombine the elements? all from one subspace on one side, from another subspace to another side. So it is lies in x0, it is lies at x1, and we know that the sum is direct. So only 0. So this is 0. Why it can be 0? For example, first, lambda equals to 0. Lambda equals to 0, x1 arbitrary, and put here 0. 1 minus 0 is 1, so x0 is 0. So all this subspace is the kernel of operator. Kernel is eigen vectors with eigenvalue 0 by definition of kernel. Second, x1 is 0. Lambda is not 0. Then x1 equals to 0. Yes? Then we immediately obtain that x0 is not 0 because it is eigenvector. Then lambda equals to 1 immediately. We want to find the eigenvector. I remind the eigenvector is not 0 vector. So one of the component x0 or x1 small is not 0. So the first subspace x0 is the space of eigenvectors with eigenvalue 1. We start with the point spectrum, but I claim that it is whole spectrum. So second, it is all spectrum. How we can show it? Construct resolvent. Let's lambda not 0 and lambda not 1, construct resolvent. And I again remind that to construct the resolvent is the same to solve this equation. We need to solve this equation. For arbitrary y, you must obtain x, the solution of this. If you can do it, so you construct, then if it is unique, exists and unique, then you construct the resolvent. So again, write this equation in components. Here we have x0 minus lambda x0 plus x1 equals to y0 plus y1. So the sum is direct, so the 0 components in left coincide with the 0 components in right. And the same with the 1 components. So we immediately obtain 1 minus lambda x0 equals to y0 and minus lambda x1 equals to y1. Can we find components of vector x0? Of vector x. x0 equals and x1 equals minus y1 divided on lambda. So vector x equals to minus lambda minus y1 divided on lambda. How you can write resolvent? Look here, please, and you can write resolvent without vectors. What operators give the first component from y? Projection pi. P. So it is. And what component gives us the second component? The additional, the complement projection. Identity minus p. So you can write resolvent in operator. Sometimes we can write only as a solution, yes? But in this situation, for projector, we can write just in operators. So you see that it is not, if it is non-trivial projector, so if all spaces are non-trivial, then the spectrum necessary 2 points, 0 and 1. It is, this space is kernel, this is eigenvalues with 1, because here is identity. So I think it is all with homeworks and projections, yes? So we can discuss the problems corresponding with Hilbert-Schmidt theorem. Okay. Do you remember that we some times ago consider such operator in L2? Who remembers the estimation on its norm? Who remembers the estimation on its norm? No, wait. One was in the space of continuous function, in L2. I remind that for any integral operator, with the kernel kxt belongs to L2 of, we have estimation that the norm of operator less or equal to the norm of this function in L2. And here the operator can be written as characteristic function of the set t less than x of t. Yep. So it is yes? No. T equals right. Yes. Here x larger than t, here t larger than x. So it's so-called operator with triangle kernel. You can understand why triangle kernel. And what is the norm of function k in L2 of 2 variables? What is the square of this triangle? It is 1 on the square. One half, but it is integral. Our norm is the square root. So we immediately obtain that remember? But norm is less. Norm is less. But now just we can find it. So problem, find the norm. Where is here Hilbert-Schmidt theorem? This operator is compact, but it is not self-adjoint. But what we know, when we prove of the spectral radius, when we calculate some task on spectral radius, when we prove the formula for self-adjoint operator, we prove that the spectral radius coincides with the norm. We obtain this formula. It equals to what? Yeah, the norm of A in square. Then idea, but this operator is self-adjoint and compact. Is it clear that it is a composition of bounded operator on compact? A is compact. We take compact operator. We take this operator. This operator will be self-adjoint and compact. By Hilbert-Schmidt theorem, it has orthonormal basis of eigenvectors, and the largest eigenvalue gives us the norm. So we take lambda 1 the first eigenvalue of this operator is norm. Moreover, without absolute value, because this operator is positive. What you can say about quadratic form? What is the sign of quadratic form? So spectrum is non-negative. Spectrum is non-negative. Do you remember that we obtained a result that spectrum of self-adjoint operator lies between infimum and supremum of quadratic form on the unit sphere? And here we see that the quadratic form is always non-negative. Always non-negative. So spectrum is non-negative. So we can take away absolute values. We immediately obtain that eigenvalues are positive. Maybe 1, 0, not 1, but maybe kernel. Maybe kernel, but and then how we can find the norm of operator A? It is square root of the largest eigenvalue of this operator, of the first eigenvalue. For many applications, it is important to know the first eigenvalue. So, first step, we need to find a joint operator. How looks like a joint operator? I'm pity. Let's come back to the integral operator. AB, kxt, ft dt in L2 AB. How looks like this operator, the joint operator, acting as a result in variable x? We calculate it when we have theme. Transposing and conjugate. As an actress. Change the order of variables as transposing and conjugate. So this operator was this indicator. It is real valued. So complex conjugation does influence on answer. But transposing must changing this by places, yes? We must write this. So T large Sx. So A star f of x is integral for T which is larger than x. So we start from x to 1. So we integrate from x to 1. So we see that it is not self-adjoint because the kernel is not symmetric. The kernel is not symmetric. So you just now try to solve the eigenvalue problem for operator A star A. Find all his eigenvalues. How we can solve it? How we can solve this problem? Let's take derivative. Question. Why we can take derivatives for functions from L2? for arbitrary function from L2, it is impossible, yes?
Yes.
But if it is eigenvalue of this operator, let's some arguments. This is equality. It is from L2. What we know about the integration of function from L2? If it is in L2 on interval, it is in L1 on the interval. The integration with different limits, with variable limits, is function from AC. It is absolutely continuous. This is function is from AC. Then again integration. So this function is from C1. So we obtain that this function is C1. Then repeat these arguments. It is function from space with continuous derivatives. It is equal to two integrals. This integral gives us space C2. This integral gives us C3. So then this is function from C3. Repeat it again. How many derivatives has eigenfunction? Infinitely. Infinite many. Because you can repeat these arguments again and again. So if you have eigenfunction, it is from C infinity. It has any derivatives. Any derivatives. So we can do it. So when we differentiate by low limits, we take away integral and must change sign. Yes. So minus integral 0x fs ds equals lambda f derivative. Take derivative again. Minus f x equals lambda second derivative. If lambda equals to 0, then f is 0. Yes, you see? So we have no kernel. So kernel is 0, so all eigenvalues are positive. So eigenvalues are positive. Because quadratic form was non-negative, but we show that if lambda is 0, then we have no eigenvector. So it is positive. So our differential equation looks like this. What is the solution of this equation? What is the solution of this equation? We know that lambda is positive, so it is sine and cosine. Yes? But differential equation is not equivalent to the integration equation. Why? Because here we lost the boundary values. From this integral we obtain immediately that f at point 1 equals to what? F at point 1. Integral from 1 to 1? 0. And from this integral equation, we are more convenient to consider the value of derivative at 0. Integral from 0 to 0, 0. So if you have a differential equation of second order, you must find two boundary conditions. The equivalent to differential integral equation equivalent to the differential equation with boundary conditions. So if second, find second boundary condition. So we find two boundary conditions. So it's better to start with derivative because at point 0 sign is 0. So f prime x equals a over square root cosine minus b over square root sine. Okay. The value at 0 equals to 0. What you can say about coefficient a or b? A is 0, yes? Sine is 0 at point 0, so we don't know about b anything. But cosine at 0 is 1. So a is 0. So your eigenvectors are b cosine x over square root of lambda. And f of 1 equals b cosine 1 over square root of lambda. It must be 0, and b is not 0. Why b is not 0? Because eigenvector is not 0. You must find non-zero solution. You must find non-zero solution. Then, at what point cosine is 0? Pi over 2 plus Pn. And lambda is positive. So n equals 0, 1, etc. The numeration starts from 0. So we can numerate lambda n equals 1 over p over 2 plus pn square where are the largest? First, lambda 0 it is. It is not lambda 1, it is lambda 0. And what is the norm of operator A? Two over pi, it is less than. Yes, it is strictly less. So, and it is a general method to calculations of the norm of integral operators. Multiplicate it on this adjoint operator, find the largest, and take the square root. Moreover, I repeat that the square root, quadratic form of operator A star A always non-negative. The spectrum all non-negative. Maybe question. If we take this operator, why we obtain the same? Again, non-zero eigenvalues coincide. For any bounded operator, non-zero eigenvalues of operator A star A and A star are the same. So we obtain the same if we consider another operator. Formally, it is another operator, yes? It's have another order of integration, and on arbitrary functions it acts in different way. But eigenvalues are the same. Eigenvectors may be different, but eigenvalues are the same. It is on your question what is classification of spectrum of AB, BA. But for example, for operator A star A and A star, the point spectrum are the same, up to the zero element, And again, the operators of left and right shifts shows us that they indeed different. Because shift and right operators are adjoined to each other. In one composition, we obtain identity and spectrum 1, and the point spectrum is 1. But in another composition, we obtain projection, and the spectrum of projection is 0 and 1. So they coincide up to the 0 element, only up to the 0 element. Do you solve at home on Jacobi matrix operator? Three diagonal. AB0, that BAB0. It is what number from homework was?
The last.
7, huh? In L2, yes? It is question on the basis. Oh, so sorry. Eigenvalues are cosine. Eigenvectors are cosine. Yeah. So function cosine p2 plus pnx and orthogonal basis. Automatically up to Hilbert Schmidt theorem. We know the standard basis sine, cosine, yeah. But you can see you might take only cosine, but with some shifts. Because it is eigenvectors for eigenvalues with simplicity 1. With simplicity 1. Idea, find the similar operator. Idea, find the similar operator. So it is operator A, L2, A, unitary isomorphism to L2 capital 0 to pi, operator B. How B looks like? Oh, sorry. I take another space. I take space from 0 to pi. Why more convenient? What is the classical basis? In L2 minus pi. What is the classical basis? Sine, cosine, or exponents.
Okay.
But sine, cosine, more convenient for our deals with this. So 1 square root of pi sine nx, 1 over pi cosine nx, and 1 over 2 pi, and n is orthogonal basis. But in L2 with half interval, you can take as basis only half of this system. So in L2 0 pi, this system orthogonal basis, and apart this system apart orthogonal basis 2 apart. Why?
But to the first, we don't need to add.
In this they are together. In this.
Yes.
At this we can take a half of system. We take half of the interval and we have half of system.
Yes, but in the first case, we don't need 1 over square root of 2p.
Yes, do not.
Don't need this.
And here it is part of cosine, because cosine at 0 is constant. Sine at 0 is 1 or 0. A cosine at 0 is constant, and this is normalization of this constant. You can consider as a part of cosine system.
Okay, but in this way, we can generate.
I take this is for cosine. For sine I don't take it.
But for sine, only we generate functions that are 0 instead x equals 0.
Oh, no. We consider the Fourier series in L2 convergences. L2 convergences is integration convergence. It is not preserves the values at points. For function from L2, the values at points, it is an incorrect notion.
Okay.
It is a class of equivalent functions.
Okay.
Why they are bases? You can take function, arbitrary function f from L2 from 0 pi. And then imagine that you continue it as an even function. If you then all sign coefficient will be 0. So you obtain the Fourier representation only in this series. But if you continue it as an odd function, then all Fourier coefficient will be 0. So this is system apart basis on this. So I take here L2 null 0 pi, and I take basis sign. So here we have standard basis ek, and here I take ek 1 here 1 over square 2 pi sine pi nx. This is En, and we construct our unitary isomorphism as following. When we prove the theorem that all Hilbert space are isometrically isomorphic, we construct this isomorphism by basis. Yes, we prove that any separable infinite dimensional space has a countable orthogonal basis, and we construct this unitary isomorphism by basis to basis, one-to-one correspondence with basis. Okay, so we take this. This is U. This is construction of U. How you can write the action of this operator in basis elements? First, in columns of matrix stays the images of basis vectors. In columns of matrix, there are images of basis vectors. Here, coordinates of the first vector, basis vector, by action of the operator A. So it is A E1 plus B A2. And for n less or greater or equal to 2, how you can write the action of operator? This is diagonal. And you have three elements, B, A, B, in neighbors. So on any vector, how it looks? How? B, E, n minus 1 plus A, E, n, and plus B, n plus 1. So you can write the action of operator B. How operator B acts on first basis element in space L2 capital. You change here basis elements because our unitary isomorphism does change the action. So it is A E1 plus B E2, but sine of 2x equals to what? 2 sine x cosine x. So we have here we have sine with normalization, and here we have sine of 2x with the same normalization, and you obtain sine x with normalization, and here sine x with normalization. So you can write it the following. Is it clear? Good. And
Professor, but you know A plus 2 don't mean a B?
A E1 plus B E2.
You is in this the right hand side. You don't A plus 2.
Oh, yeah. Sorry. B. You're right. B, of course.
Okay.
Okay, so here B. Okay. I agree that any element have this normalization, so I take it away. Here A sine n minus x plus here B plus A sine nx plus B sine n plus 1 x. Do you remember the school formula for sign of difference and sum of arguments? Here sine nx cosine x minus, and here sine nx cosine x plus the same. Coefficients are the same. So what happens with these parts which I don't write? Because they are not important, so they are reduced, so I don't write it. So we obtain that it's again the same function. So it is so what operator B do with any function from L2 capital? If it multiplies any basis element on the same function. So this matrix is similar to operator of multiplication of function. What is the spectrum of this function? Is value of this function. It is continuous function. And when x goes from 0 to p, cosine takes any values from 1 to minus 1, yes? So the spectrum of operator B equals R a minus 2 absolute values of B, 2 and it is continuous function, continuous spectrum. Because our function periodic, it is not constant anyway. Any values takes must 2 times for cosine, at least. So we measure 0, so it is continuous spectrum. So it is continuous spectrum. And one more application of Hilbert-Schmidt theorem. Mm-hmm. So for operator A is the same answer. The same answer. Again, come back to the Hilbert-Schmidt theorem. Let A is compact in some Hilbert space. Then is self-adjoint and compact. Yes? By Hilbert-Schmidt theorem, exists EK and we know that gamma k are positive, yes, or non-negative, because quadratic form, non-negative. Define new numbers. We can take square root because lambda k non-negative. Non-negative. These numbers are named as numbers of operator A. As numbers of operator A. and definition. If sequence Sk lies in LP, small, then we say that operator A belongs to class S capital P. It is Neumann Schatten class. Maybe here, Apo, Schatten. Here, Schatten. The more important classes at S1, it's so-called nuclear operators. Nuclear. It's operators with finite determinant. We can write for these operators determinant. It is finite. Or it's so-called trace operators. You can define trace of operator. Traces of operator is sum of quadratic form A1, AK, AK. And for class of S1, it not depends on orthogonal basis EK. EK is some orthogonal basis, orthonormal basis. And I repeat it, for class S1, it is does not depend on basis. Then class S2, it is so-called Hilbert-Schmidt class. It is Hilbert-Schmidt class. Hilbert-Schmidt class.
Sorry.
How I write it?
The trace of S1.
Trace operator.
Is what?
S1.
Is defined.
That
Okay.
is definition. S1, it is notation for the name of class S1, it is trace operator.
Okay.
Trace operator. Class S2 is Hilbert-Schmidt operator. Class S infinity, it's all compact operators in Hilbert space. Class S infinity, it's all compact operators. Do you remember that we proved that all compact operators in one space, it is two-side ideal? These classes S1, S2, etc., SP, it is an ideal too. But they are not closed. They are not closed. If you try to find the closure, you obtain all compact operators. So it is some classification of compact operators. So it is some classification inside compact operator. We take arbitrary operator from in Hilbert space, yes? Arbitrary compact operators in Hilbert space. Then by Hilbert-Schmidt theorem find lambda k, then find S numbers. And then classify all compact operators by the property of this sequence S small, S numbers. If it lies in LP, we call that operator lies in class LP, SP, Schatten class. It is ideal, but not closed. A two-side ideal, two-side. So multiplication of bounded operators on class SP, it is class SP. But the closure of SP in norm, it is all compact operators. They are not closed. So for some perturbation theory, it is interesting to consider compact perturbations, and sometimes it is interesting to consider perturbation in class of Neumann-Schatten. So that's all for today, and now let's write homework. First homework, find the Schmidt representation for any compact operators in Hilbert space. First. I think I forget how to write Schmidt. A is compact in Hilbert space. I write Greek letters. It may be finite sum or infinite sum. It depends how many non-zero S numbers you have. If operators has finite non-zero S numbers, so the sum will be finite. If it has infinite number of S numbers, the sum will be infinite. So where phi k is orthonormal basis and psi k is something orthonormal system, not basis, but orthogonal system. Find eigenvalues it is, do you see that the kernel is symmetric? Minimum. Kernel is symmetric, so operator is compact and self-adjoint. So you can find eigenvalues, eigenvectors, and find class SP. Describe to what class SP it belongs. And third, unfortunately, I forget one of the operator, but I hope I correct. So it is formulation if you want to put an exam 2 for student. I thought problem is have different formulations. If you want to take away students from exam, you can formulate it in the following manner. Let mu k is solutions of equations. It is from graphs, we can see that it has a lot of countable many. For mu positive. Then is orthogonal system, but not basis. Additionally, consider it has one solution. Together, cosine and hyperbolic cosine are orthonormal bases. Is it possible to prove in this way? Another formulation, third. Consider operator here minimum maximum and try to find ek and lambda k. Here you don't find the precise. If you try to find lambda k, you must obtain these equations. The problem is that for maximum you have series for positive eigenvalues and one negative. and one negative. So if you consider only positive, you obtain this, but you lost this. So it is not basis because you need one additional function, cosine hyperbolic. So that's all for today.